Okay, so I would like to figure something out about half-lives.
Yay.
Okay, and I don't remember what the exact, I don't remember exactly what the chemistry phrasing of this question is. So I'm going to phrase this question in general, and we'll figure it out, and you can use this
however
rule.
long it takes for half of the material to decay.
No, I don't remember what half-life is.
Oh, I don't know what you didn't.
So what I don't remember is which constants go where in chemistry land, or what letters they are.
I have it.
No.
Okay.
No, half the fun is discovering.
Yes.
Yeah, I think 2 B's and then we had to work it out.
Okay, what do you got? Hit me.
The natural log of A at T. Well, it's like in brackets. Because it's a, yeah. And then close it, and then below it is T. I like subscript.
Subscripts.
Yeah. And then A naught, so A subscript 0. Below it. Sorry about that. But in brackets too. All equals negative K T.
Right.
We're not supposed to be in the
The A naught's in the brackets, or
No, you
like this?
That's right, yeah.
Okay, so what does this thing represent? I have a guess. Let me guess. It'll be fun. Tell me if I'm wrong. So this whole thing is the amount after time t,
Yeah,
and this is the initial amount.
yeah.
Right?
Mm-hmm.
And K is kind of the thing you're interested in, right? That's the decay rate.
The rate of
Yeah. Okay, so let's fiddle this around and see the exponential function. So my claim is if you take, wait, I want the exponential function, right?
Yeah.
So I have a log. I would like to turn that into an e to see the exponential function, right?
Cool.
Yeah.
You guys with me?
Yeah.
Okay, so, oh, you lied to me.
Me?
It's like this, isn't it? Let's go with it is like that. It should be like this. So the reason it should be like this is that I want to see that exponential function, right? So the first thing I'm going to do is I'm going to hit both sides with an e to the stuff, right? So I got the amount of chemical A at time t divided by the amount of chemical A at time 0 should be e to the minus kt, right?
Straight up.
Then I multiply both sides by A naught, the amount of A at time 0, and I get the amount of A at time t is the amount of A at time 0 times e to the minus kt. That's your exponential function, right?
Yeah.
You guys see that? How would I put this into more mathematical notation? Like, what's the only math thing that's kind of missing here?
Well, you then linearize it, and then you like.
No, don't do that.
No? Well, that's what we do.
F of x.
Yeah, so you could linearize this and make some
So you make
approximation.
it so f of t
But I think maybe the math thing
is like f of a of t.
would be, instead of saying that this is a t sub t, I would call that the amount as a function of t,
Fair. Yeah.
right?
Equals
And I would probably drop these funny brackets.
equals the amount e.
But yeah, otherwise this is exactly the thing I would give you. Right? This is the default model for radioactive decay, populations, and continuous interest. Okay? This is what's called a PERT model. Why is it called a PERT model?
It's
Yeah,
pertinent.
because usually it does populations, and population starts with a P, not with an A. Right, so the usual phrasing of this model is P of t is P0 e to the minus RT,
Oh,
or
that's what it's called.
positive RT, the PERT model.
Oh.
That's what I'm thinking about population growth, right?
Pertinent.
In chemistry class, I'm usually thinking about decay. Because I'm thinking about the amount of unreacted substance or the amount of undecayed stuff or whatever. So, up to context at least, you're looking at one of these two things.
That's cool.
Cool?
Yeah.
Alright.